Welcome to another video for chemistry, and in this video we're going to be discussing acid-base reactions. So in a nutshell, what this video is about how a hydrogen ion is passed or are passed from one molecule to another. So what is a hydrogen ion? Hydrogen ion, if you look at the periodic table at the top left, you're going to see the hydrogen atom. The hydrogen atom contains one proton, as indicated by our atomic number here, and one electron. That one proton and one electron will give an overall charge of 0 to hydrogen. But you'll notice that in our equations that we work with, you're going to see the hydrogen with the plus sign there. That means that this species right here, hydrogen ion, has a charge of +1. And the reason why it has a charge of +1 is because this particular species has the electron missing. So you have one proton and no electrons. So essentially, a hydrogen ion is basically just a proton, and that's it. So that's why you'll hear sometimes an acid or a base being referred to as being protonated. That just means that there's a proton that's been attached to it, or a hydrated proton, meaning that a proton has attached itself to a water molecule, an H2O molecule. Alright, well there's two ways to define an acid-base reaction, and definition number one that we're going to go into was developed by a Swedish chemist called Svante Arrhenius, and he won a Nobel Prize for his work in 1903. And what his definition of an acid-base reaction basically is a substance that ionizes or dissociates in water to produce hydrogen ions, and that would be the acid, and a base would be a substance that produces a hydroxide ion by OH negative. But this definition is limited to just aqueous solutions. So we're going to go into a second definition, or a more complete definition of an acid-base reaction. And this reaction was proposed by a Danish chemist named Johannes Bronsted, and this was in 1932, so about 30 years after. So how he defined an acid, or what we'll call a Bronsted acid, was as a hydrogen ion donor, something that gave away a hydrogen ion. An example of that we find if we look at hydrochloric acid in an aqueous solution. Okay, hydrochloric acid in an aqueous solution, when poured into water, will dissociate into a hydrogen ion and a chlorine ion. Okay, so hydrochloric acid is our Bronsted acid, and that's because it is donating a hydrogen ion, okay, which is indicated right there. Okay, that is our hydrogen ion. And a base is one that accepts the hydrogen ion. So if we look back at our equation, our previous equation, that hydrogen ion is being donated by hydrochloric acid. Okay, that is our donor. But the question is, who is accepting this hydrogen ion? Keep in mind that this reaction is in an aqueous solution, which means that there is water involved. Okay, so what ends up happening to this hydrogen ion is it attaches itself to an H2O molecule. And H2O plus another H gives us H3O, or a hydronium ion. Technically, this is the more correct way to write it out, but we write it out, and you'll see most texts write it out as a hydrogen ion floating by itself in an aqueous solution, when technically it actually attaches itself to water. So keep in mind that if you see hydronium, H3O plus, or a hydrogen ion plus, they're technically the same thing. Okay, even though that's more accurate than this symbol here. Alright, so let's look at our Bronsted acid. Again, this is our donor, and then our acceptor in this case is H2O. That is our Bronsted base. So our Bronsted definition, again, okay, our definition number two is Bronsted acid donates the hydrogen ion, and the base, the Bronsted base, is any ion that accepts the hydrogen ion. So let's put on our atom goggles, and let's take a much closer look at what is actually happening in this particular reaction that we just spoke about. So let's look at hydrochloric acid on the left and a water molecule on our right. But let's first take a look at at the way electrons behave in this particular molecule. So chlorine is a more negative molecule. It's more electronegative. It is more electron hungry, whereas hydrogen is less electronegative. Okay, so because chlorine is more electronegative, it's going to pull the electrons from, and it only has one electron now, hydrogen does, it's going to pull that electron towards the nucleus of chlorine. So you're going to have more electron pull. So if there was a tug of war of electrons, because chlorine is more electronegative, it's going to pull the electrons more towards chlorine. It will have more of an electron concentration, which means that the side that the chlorine is on is going to be more negative, and because hydrogen is losing an electron which is negative, so if I'm losing something negative, I'm going to become more positive. So you have this side of the molecule that becomes positive and this side of the molecule that becomes negative. So I have an arrow pointing towards my negative side, which is where the electron is going, and you'll notice here I have a little dash here showing that this end is my positive end. Okay, so that's what that symbol here signifies. So let's take a closer look now at a water molecule. A water molecule is more electronegative on the oxygen side. Oxygen is more electronegative, and again, hydrogen is not an electronegative atom. So that means that you're going to have more pull towards, again, that tug of war. Even though there's two hydrogens to one oxygen, that oxygen is strong enough to pull the electrons from hydrogen towards its own nucleus, giving oxygen a negative charge, and then the hydrogens will have more of a positive charge. So this is what we call polar molecules, meaning or a polar relationship, meaning that at each end of the molecule you're going to have different charges. You have one side of the molecule that's negative and the other side that is positive. This is very important to understand when looking at the behavior and why hydrochloric acid dissociates in an aqueous or water solution. So if I have hydrochloric acid on the left and I mix it with water or liquid on the right, and you always pour the acid into the water. So when hydrochloric acid goes into water, you're going to find that all the positive ends of water, which is hydrogen, are going to attach to the negative side of the hydrochloric acid, which is chlorine. Remember, in chemistry, positive negatives always attract, opposites always attract, and like charges always repel. So you're going to have the negative charge of one molecule be attracted to the positive end of the other molecule, and vice versa. So notice here how hydrogen, the positive end, is attracting all the negative oxygens from the water molecule, and then the negative chlorine is attracting the positive ends of the water molecule. So let's get a more magnified look. So again, you'll notice here at all the positive ends, okay, all the positive ends are attaching, or all the negative ends here are attaching to the positive end of the hydrochloric acid, and then all the positive ends of our water molecules are attaching to the negative aspect of hydrochloric acid. Okay, so let's look again on the other end. So again, opposite charges attract. Okay, so what will end up happening is that these opposite charges will attract to another opposite charge of the other molecule, and what will end up happening is that there's going to be enough of a pool that you're going to end up separating or dissociating hydrochloric acid to a chlorine atom and a hydrogen atom. So hydrochloric acid is going to donate its hydrogen atom to water. Okay. Now what will end up happening with on this side in particular, on the left, like we discussed before, technically this hydrogen atom doesn't float around by itself like chlorine does. Chlorine will now float around in the aqueous solution freely, surrounded by hydrogen atoms, or the hydrogen side or the positive side of the water molecule, and it'll just dissociate and float around in this aqueous solution. Now hydrogen, it doesn't necessarily float around. It actually attaches itself to a water molecule, making hydronium atom, like we discussed before. And this is what the hydronium, the H3 molecule, looks like. Okay, so in this case, water becomes our Bronsted base because this water molecule is accepting the hydrogen ion. So it is a base. And our chlorine, hydrochloric acid, is our donor, which is our acid. Okay, our Bronsted acid. Okay, well that does it for a look at acid-base reactions. Good luck in your study.